Hi. Today we're going to see the class of today is going to be related with risk analysis and expected monetary value. So I hope you enjoy it. Okay. And we are going to be this part of the course is related with bringing the part of probabilities into water resources management. So in order to do that, well, we're going to need to have some specific, we'll have to do a quick review of some of the statistics and probability. This is very simple. Actually, if you know how to count, this is a way of how to do it. So the first thing is the mean. In this case, the mean is you add all the numbers and divide by the n members. In terms of the weighted mean, well, in this case, you add the you have a specific value, and then you multiply it by a specific percentage or weight. In this case, for instance, and these are the medians. We're going to be using in our a lot of this presentation. We'll just talk about this, which is the weighted mean. You're going to see. Why is that? We can use a specific value times a probability. So this might be a probability of something. So we will, what actually we're going to do with this weighted will be a specific event times the probability of this happening. Okay, and well, of course, then the median, which is parameter as the mean. Okay, so in terms of precipitation, here you can see that, okay, imagine that we have a precipitation of, we have a basin, and in this basin, that is this one, it can be divided in three different areas. Area 1, Area 2, Area 3. In each of these areas, we may have a precipitation, let's say, of 11, 15, 20 inches a year. So we say, okay, in this basin what we have is the sum of the precipitation over 3. So our mean precipitation will be our arithmetic precipitation will be the sum of this over 3. We do this doing a weighted mean. Well, basically what we're going to do is to multiply each of these precipitation values by its area, and then we will divide it by the overall area. So in this case, the precipitation of 1 times the area of 1, which is this, plus the precipitation of area 2 times the area of 2, plus the precipitation of 3 times the area of 3, which is what is going on here. And all of these divided by the total area. So what you're seeing here is that we are weighting each of these precipitations by the extent, by the area. And in this case, the weighted mean, the weighted precipitation, it will be 13.2. So it kind of helps us understand how things happen, but depending of the magnitude of what we are waiting for. Okay. Something interesting is that what you're gonna find out is that most of the things that we analyze, they have a skew to the right. So basically, they have this at the beginning, this high tail, well, this increase, and then they have a tail to the right. Why? Because most of the things that we measure does not go to the negative side. The other part to be important is that usually the mean, because of these large values, the arithmetic mean overestimate what is a central measure of this distribution, with the median does a better job. So just consider when you're doing means that sometimes we overestimate things. And this is an example of this. If you have this, and you're doing, this is the arithmetic mean, the regular mean, and this is the median. So here we have the median, and in the other one we have just the mean. So if you do the mean of this, it will be 8.1. If for some reason you have a typo, then you will have a value that it will be way larger. With the estimating the medians, you can see that the value is the same. It is a very consistent or robust measure. The only time when the mean and the median are the same is in a normal distribution function, the one that is the Gaussian distribution when you have a bell. So that is the only time when the mean and the median are the same. And then we have some distributions for spreadness, how the data spread out. And one measure that we usually use is the variance and the standard deviation. The interquartile range, basically you obtain the percentile 75 minus the percentile, in this case this has to be 25, and then you obtain here what is the interquartile range, and the median absolute deviation. Now this is again with this series of data, you obtain this, which is the variance, and then, well, of course you can obtain the standard deviation, and this will be the same for another one, but with this type. And you can see that, so here you have 120 compared to 12, so you can see that the interquartile range is more robust compared to the standard deviation. Okay, and then histograms. And basically this, we have a bunch of data, and let me see. So histograms are just kind of tell you what is the frequency. So in this case, for this range, and this is annual stream flow from, let's say, a little bit of 750 to 1750. The frequency of this flow happening in this river is about 7 times a year. Of happening between this range, it will be about 15 times. Happening between this range, it will be about 21, 22 times. And so on. So you can see that actually what this means is you just count how many times this is happening, and this is an histogram. When we start adding, so we have this first frequency, and then we add the first plus the second, and then we add the first plus the second plus the third. This is what is called a cumulative distribution function. We're accumulating the probabilities. This is something that I was calling here the quartile plot. This is a different way of actually seeing how this is distributed, which basically these are box plots. So this value here, and this is something that you have already seen for the evapotranspiration for, in this case, different crops in Pájaro Valley. And part of that, what this tells you is this is the median value, this is the 75th percentile. Below here we have the 25th percentile. And this is the minimum value and this is the maximum value. What does this mean? That, okay, for a grower, for a farmer growing vegetables in Pájaro Valley, sometimes the minimum value that they can use is 1.65 acre-feet per year in their field. Usually, I mean, 50% of them use something in between 2.19 acre-feet per year to 3.8. This is 50% of the population lives here, then 25 in this area and 25 in this part. This is the median value, which is 2.67. And there are persons that use as maximum 4.13. So this is what these box plots charts tell you. Now, let's talk about a little bit of random variables. And basically, we have something that is, well, random variables basically comes in two flavors. You can have a discrete random variable, and basically what you can have is these different histograms or histograms that have this kind of box or bars distribution. Okay, now if to this type of data you fit a distribution or an equation, well, then what you have is these guys here, which is a continuous random variable. Why this is called discrete? Because it basically just goes from this value to this, it kind of jumps, that's why it's discrete. This one is continuous because it has a continuous equation going through this to the representation of this function. Okay, now we have two different types of seeing this. So basically when we have this and we do it, this is in terms of how frequent, we're counting how many times this happens. When we do it in terms of probability, and if it has this, it is composed by a line, this one we call it PDF, probability density function. If this is composed by a series of bars, as the one that we were seeing before, we call this a probability mass function. And that's basically the difference between these two. That this is composed by a series of line by an equation, and in each equation we have all these different pieces that are called kind of differentials. And when you add all of them, that's why you are integrating here. All of these has to sum to 1. It is the same here. When you add all these different blocks, all these different bars, all of them must add 1. So that is the only difference. When you start accumulating, similarly, if you accumulate this first graph and then you accumulate the first one plus the second one, and then for here, so this is number 1 here, 1. This is 1 plus 2. This is number 2. And then you can do the same for 1 plus 2 plus 3 here. Okay? So what you have here, you start accumulating this data when you have CDF, cumulative distribution functions, which are these. And again, with these ones, you can create or fit an equation. These, because these are discrete, they have this kind of these values that are, you can imagine this kind of as a bars, some bars here. So anyway, so that's how this look in essence. I think as I mentioned before, we're going to be talking about, this is expected monetary value. We're going to estimate what is the expected value of something. In this case, we're going to use this equation here, which is what is the expected value of a variable, that in this case is x. So we have expected value of a particular variable. And basically what it tells you is you need to multiply the value of that variable times the probability of that value happening. Again, this can be, let's say, money. What is the probability that a specific event related with a certain cost happen? So here is the probability, and you multiply times the money. Or it can be the level of a reservoir. So the probability that a level happen times that level of the reservoir, and so on. So in essence, is multiplying a value 1 times the probability of that value number 1, plus the probability of a second value times, well, the value 2 times the probability of that second event, and so on. So that is basically what we're going to be talking about when we refer to expectation. Now, this is done because we are not sure, or well, it's not that we are not sure, but we want to cover a range of different possibilities, different things that can happen to a design or to a policy that we are trying to implement. So in this case, what we are trying to consider are the uncertainties, and because of that, we are using this expected or expected monetary value. So let me show you a small example. So we have the elevation of a reservoir. That this one vary every year, so it can be very empty or a little bit more full or so on. So let's start with this. The pool level here can vary from 50 to be very full to 10 feet that can be very, very empty. What is the probability of that happen? Well, you just record how many times these have happened over the overall period, and then you start saying, well, you know, it happened, let's say in this case, a pool of 10, it happened 10 times out of 100 times. The level 20 happened 25 times out of 100 times, and so on. So the probability, remember that one of the golden rule of probabilities is that the probabilities, all of them must add 1. So let's say, what is the average pool level? If I'm telling you that, okay, here we have happened a pool of 10, it happened 10% of the time, 20, 25% of the time, 30, 30%, 40, 25% of the time, 50. So how can we estimate this? Well, we just basically multiply this, the level, times the probability of happening, plus this second level pool times this probability, plus, which is what I'm doing here, this 10 times the probability of that happening, then 20 times the probability of this happening, then plus 30 times this, plus 40 times this, plus 50 times this. So at the end, the average pool level is 30 feet, which is just basically doing that. For the average visitor rate, you exactly need to do this, the same. What is the probability? Well, what is the visitor rate times the probability of that happening, which is here. Then what is the probability of 75 visitors happening over this? So you have it here. What is the probability of 100 happen is this, and so on. So at the end you have what is the number, we can have what is the expected average visitor rate. What is the expected visitor rate? So on average, we have 78.25 visitors per day. And this is why this is important. Well, if you can estimate, given these probabilities and how many, the number of people coming to the, in this case, to the to this part, to this reservoir, when then you can say, well, and if we charge $10 per each visitor, so we're expecting that on average we're going to receive $783 a day. So that's why this is important. So now we're going to be talking about this exercise, and I'm going to be using this exercise for the second part of this lecture. Basically, what we are going to do here is, okay, we have two different weather conditions, which is it can be wet or it can be dry. And depending on if it is wet or if it is dry, we have, for that pool, we have, no, for this, for a specific state park, these are the recreational benefits that you can get. So you can get about 100K when you have a wet year, and the probability, okay, so when there is a wet year, you can have certain benefits that will go from 100K to 150K to 250K for this state part. Okay, so at the end what we really want to know is what is the expected, what are the expected benefits out of these different weather conditions and recreational benefits. So this is, I'm going to be talking about this exercise through this lecture presentation. This is, we can calculate it, and it's going to be 170K. Okay, that is the expected value. How I get to this result? Well, basically, I construct this, which is a decision tree, and in this decision tree, I was able to estimate this value. Why a decision tree is important? Well, because you can know what is the probability that it will be wet or it will be dry, and these are called marginal probabilities. The conditional probabilities that you receive these benefits given that it's wet, or these benefits given that it's wet, and so on, similarly for dry. And what is the probability that these two events happen, which is this. Now, in order for us to construct this, we need to be able to estimate three different types of probabilities: marginal probabilities, conditional probabilities, and joint probabilities. I know, and now you're going to be like, oh wow, so many probabilities. Don't worry, I'll show you how to calculate it, but that is the overall purpose of this, that at the end you can build something like this, a decision tree, and be able to construct it using all these different probabilities. So let's start with the joint probability, with this one here. What is a joint probability? Okay, it's the probability that two variables happen at the same time. So what this means is that the probability that x and, the comma means and, y happen. So in this case here, what is the probability that in this case x1 and y1, or the probabilities that wet and recreational benefits 1 happen, is 0.1. What is the probability that dry happen, given that we have these recreational benefits 1? So it is 0.1. At the end, what you can see here is that we can estimate, well, I give you this table where this is just pretty much counting the events, but you can see that the recreational benefits to happen given that it's wet is 0.2. The recreational benefits 3 happen, which is very large. Given that it's wet, it's this much. Okay, at the end, remember that the golden rule is that when you add all of these, they must add to 1. Okay, and the other important part here is that, well, what we are saying, and this is an assumption, that we have 2 random variables and they are independent. What that means is that when an event X happens, this event is not influencing, and that this other event Y happened. So that these benefits, that the weather does not depend in people coming, or vice versa. So this is a big assumption. And what this means is that these two are independent. There are very few variables that might be independent, but for the terms or for the sake of doing some of this math, that is important. Why? Because if these two are independent, then the joint probabilities, these joint probabilities can be obtained by multiplying the marginal times the conditional. So that's kind of what this means. If they are independent, you can multiply the marginal times the conditional, and you're going to get the joint distributions. So now, the following one that I'm going to talk about is the marginal distributions, which is this. So before I talked about this, now I'm going to be focusing on this one. So The marginal distribution, so these are the joint distributions. Now, the marginal is what is the distribution or the probability of x if we just ignore or don't pay attention to y. In this case, what is the probability that wet happen regardless of this? In this case, we know that the probability that wet happen is adding these 3. So if we add these 3, we know that the probability of wet happening is 0.4, 40%. What is the probability that dry happen or dry weather happen? In this case will be the sum of these 3, which is 0.6. So at the end you can see that this marginal distribution or marginal probabilities is identifying what is the probability that wet conditions happen without considering the variable y. Again, remember that the golden rule in probabilities is that the sum of the probabilities should be equal to 1. And we can do the same. What is the probability that recreational benefit happen? So the probability of y, we can get the marginal distribution of y, and in this case we'll be obtaining what are the probabilities of these 3 happening regardless of the weather. So in this case it will be the marginal distribution of y will be in this case 0.2 for RB1. In this case it will be 0.5, and in this case it will be 0.3. And if we add all of these, the golden rule is that all of the probabilities must add equal to 1. So this will be the marginal distribution of y. This one here is the marginal distribution of x. This is the marginal distribution of y. Okay, now the following one, so we know what does this ones mean, this, and now we're taking a look at the conditional probabilities. So what are the conditional probabilities? Well, basically is the probability that x happen given y. The probability that this happen, and this bar means given that something has already happened. Okay? So in this case, let's see, what is the probability? Okay. What is the probability that the benefits won't happen given that the condition is wet? So wet happen. What is the probability that we're going to have benefits number, recreational benefits number 1? So in this case it will be dividing the marginal probability, which is this 0.4, over the joint probability. When I think about these conditional probabilities, I think it in terms of what is the in terms of percentage. So given that wet is a 40% chance, out of this 40%, 0.1 is recreational benefits too. So it's 25% or 0.1 over 0.4. Of this happening is 0.2 out of a 0.4 probabilities. So it's 50% that this happened given that it's a wet condition. And this is again, out of this 0.4, 0.1 comes from this recreational benefit 3. So if you do this, is 25% that this happened. And again, the golden rule is that the sum of all of these must be of 0.5, 0.25, 0.50, and 0.25 must add to 1. So given that it's wet, that we have wet conditions, there is a 25% probability that we're going to have recreational benefit number 1. there is a 50% probability that we're going to have recreational benefits too. There is a 25% probability that it's going to be recreational benefits number 3. So now, as you can see, this starts kind of making sense in terms of seeing all these probabilities. And we can do the same with dry. So the probability of dry will be 0.6. And what is the conditional probability that given that it's dry, we have recreational benefits at 1, it will be 0.1 over 0.6. In this case, for RB2, it will be 0.3 over 0.6. And in this case, for recreational benefit 3 will be this. So that's how we can estimate it. So basically, this is what happened. The conditional distributions. So the joint distribution can be obtained by multiplying the marginal, which is this, times the conditional. And for making this, remember that we make the assumption that these two variables are independent variables. And then we can estimate, if we know how to do this, well, if we want to estimate this, which is the marginal, then we divide this over this. Or if we want to estimate the conditional, then we divide this, which is the joint, over the marginal, and so on. So this is how you now start seeing that the marginal distribution is this, the conditional is this one, and then with this equation we can start obtaining, if I give you the joint distribution, then you can start estimating what is the conditional and the marginal distribution. So let's go back here. This is the problem as we started, and remember that we start this problem by saying, okay, there are different recreational benefits associated with the weather. So what are the expected benefits, considering that we have different weather conditions and different recreational benefits? Well, remember that when we were talking about this expected monetary value or this expected value, you multiply the probability times the outcome, in this case recreational benefit 1, then plus probability number 2 times the recreational benefit number 2, which is this, plus the probability number 3 times the recreational benefit number 3, which is this. You can see it here. This is where I'm going into this equation. Then plus probability number 2 times the recreational benefit number 1, which is this, and so on. So probability 3 times the recreational benefit number 3, and probability, and this one of 0.2 times this recreational benefit. So if you do all of these, you're going to get 170k, which is what I was mentioning at the beginning here. Okay, now this is how to go directly to the result, this procedure, and this is okay. Something that actually is very useful is to know how to build this decision tree. Why? Because if once you kind of learn how to read this, it's actually very useful. So the first thing that you can notice here is that there is a 40% that the weather will be wet, or 60% that will be dry. This, if I give you only this information, you can estimate what is the probability of wet. Why? Because you know that if you add these 3 numbers is what is going to give you wet. If you add these other 3 numbers is the probability of giving dry. So if you have, what is the probability of wet? I give you these values are given through this table. So what is the probability of wet? Well, we add this plus this plus this, and we have what is the probability of wet. If we add for dry, it will be the same, this plus this plus, well, these 3, and that will be the probability of dry. And you can see that I put all these numbers here. Once we have these 2 values, we can estimate what is the conditional. which is basically this over the marginal. In this case, it will be 0.1 over 0.4, and that will be this value here. This will be exactly the same, 0.2 over 0.4. And this is interesting because, okay, once you know that you are in a wet condition, you can say, okay, the probability of me receiving, or this park receiving a lot of money is 25%. There is a 50% chance that we're going to receive 150, and there is a 25% chance that the recreational benefits will be small, 100K. If we are in a dry condition, there is actually 17% probability that it will be, the benefits will be small. There is a 50% chance that it will be this much, and there is a 33% chance that it will be very large benefits. So now you can see why this is still helpful, because you know what is the probability of the weather conditions. You know once you're in a condition what can happen, and you know that at the end, overall, what you expect to of the benefits is 170K. So that is why this concept is very useful, because you do not only know what is the expected overall, what is the expected benefits, but you know that you might be in certain conditions and what will be the potential outcomes that will come. So that's why this is important. Okay, with that, I think that's all for now. You're gonna have an exercise related with this, so you can always come back to this and see how I estimate all these different joint, conditional, and marginal probabilities. Have a good one. Bye bye.